Thank you for having me. Um, Good morning, everyone, I guess. I Please cut me off if I go off tracks or if I go over time. This is my long title. I'm going to talk about substrate-dependent mathematics, and probably I should have taken a shorter title, something like this. But here we go. Um, right. So I'm based in Japan. I have a couple of slides to introduce what I do here. So we study the future of intelligence that involves artificial and natural intelligence, and we are embedded in the most of what I do is embedded within artificial life as a frame, and we do various things from distributed cognition to things more connected to awareness and consciousness-related kind of research. And it's mostly at the intersection of three things. Most of you, if you know me for my artificial life side. I do machine intelligence research, and also I'm interested in this neurophenomenology kind of research. And I think that in order to understand intelligence, you have to look at the intersection of all three and not ignore one part of the puzzle. I think that's important. And yeah, that will um, come into frame very soon in my presentation. Um, so this is a topic I've been talking about with some of you for quite a while now. Does mathematics exist? Has it been invented or discovered? And I've seen um, Mike's talk, and I guess we've been talking about that for a while now. And yeah, I'm very happy to share a few thoughts with you. They're going to be very disorganized. They're going to tackle whether we invent this map. Is it the map of mathematical language versus a territory? Um, is there some kind of implication of us being agents within this sort of simulation kind of thing, experiencing mathematics? And how much agency do we really have? And there are usually those two camps, and you recognize the faces. Let's call them the idealists versus the empiricists, Plato versus Aristotle, more or less. I'm going to try and sidestep this this usual picture. And maybe this is so I spent some time at the Institute for Advanced Study, and the motto they have there is truth and beauty, and feels like it's really talking about truth versus beauty in a way, and I'll come back to that. This is the menu for today. I'm starting with talking about layers of reality, and I'll finish with how to make first contact with the Platonic space, a bit like we make first contact with um, alien mathematics in a way. All right. I'll take a metaphor for this talk, and it's going to be my favorite metaphor, the game of Go. I don't know how many of you, I can't see your faces because that's not working, but um, I don't know how many of you know the game of Go. It's a bit like chess in a way, and we are trying as humans and as scientists to figure out the rules of the game, the dynamics of this universe by looking at the pieces move. And we're sort of playing with this sort of God figure on the left, which is here an Oni, this red color protector. And they have those superpowers, super sight that we don't have. And we're trying to just figure out things from our own senses and being embedded within the world. It's often represented, reality is so often represented as being layered. So if I take the game of Go as one of those layers, you have an algorithm that would produce it. You see that I'm showing a few features of the game of Go, and it's mostly a sort of subjective experiential kind of features that I want to highlight here. So the notion of life and death, different notions in the game, influence, thickness, all of those kind of strategic things that you feel as a player really playing the game is what I want to highlight. And I want to start this way from experience. And you have the circled in red, move 37. And those moves feel like something, and the dynamics are in there in that layer. And you don't really have to go down in other layers, which is why it's emergent into the algorithm. And yet the algorithm, whether human or here AlphaGo or AlphaZero, play the game and actually make the dynamics unroll. A code produces, implements that algorithm, and you can have as many levels of description realizing this reality as you want, down to physics, which can be more or less coarse-grained and fine-grained. I think this kind of picture is sort of helpful and helps us understand how we have different languages that really allow us to play reality and understand how it's being played, like this game. That's why I have this playfulness in there. And I'm doing research with a few philosophers about this playfulness, and that's how it's connecting to this part of my research. At the top, somehow, you have those pure concepts, right? And we have those constructs, those world models that we build from different fields, and they're supposed to, ideally, fuse together very nicely in a unifying theory of everything that allows us to explain, describe reality. And at every level here, I list a few of those scientists contributing to this field. We built those world models, and yet we also have to deconstruct them to unify things with other models. And we have to do it also to connect with other minds, because science is intersubjective. We tend to forget that. We tend to think, I tend to think that it's objective when I practice it. And yet, here I want to highlight that, come back to everything comes down to the experience of events and phenomena. And in particular in Japanese philosophy, in different approaches here in Asia, you talk of pure experience, the exercise of trying to come back to the most basic kind of experiences that you can have that make us us. And I must say, I'm not very knowledgeable about this field, but I think it's very important. Edmund Husserl, with his psychological theory of phenomenology, has attempted that, and I think it's a very worthy sort of adventure. Now, to transfer between those levels of descriptions and also sidestep, it could be, it doesn't have to be purely hierarchical in the simple way that I have drawn it here. You can use different types of tools and translations, functorial mapping, so category theory, etc. And I think what we are trying to reach is a sort of lingua franca of intelligence, understanding reality from the roots of experience. But interestingly, I think this also loops around. And I was also interested that in Mike's essay when he mentions that same loop. So yeah, that's something that I'd like to discuss and hear about in this series of talks. But essentially, the pure concepts that we abstract away and away from the basic phenomena that we experience in physics seem to connect, to loop back at the end with the abstraction of pure experiential events. And there are different intuitions that have been pointed out by various philosophers over time. At the end of the day, we're trying to find a universal language to describe all of reality, and sort of natural to point at something Platonic something Platonic space-like in the way that we describe it. Now, what about this substrate dependency? Does everything have a sort of constraint in what it is embedded by or in? Or is it independent? Like we're used to talking about mathematics as something pure, like Kant and all the guys on the left earlier. And yet it seems like where the computer that simulates you seems to be constrained by the sort of hardware. So how do we escape that? And there are different I's, from I intelligence to artificial intelligence, human, etc., ASI. And I want to talk about more and more diverse frames of seeing things with different possible substrates for those types of intelligences. So I'm referring to sort of the image of Stephen Jay Gould here, where we are trying, if we were to run again the tape of life, what would we get? It is very unlikely, it seems like, that we would get exactly the same type of intelligence we already got. So what about all the other types of intelligences? And maybe like Stephen Wolfram likes to say, do they lead to different types of mathematics as well? And it's very probable in his view. Does that mean that there is no Platonic kind of picture in frame? So this connects with my kind of research that I work in and promote. So maybe if you, in case you've never heard about artificial life, there is a conference coming up. I'm chairing it, and I'm also the president of the society. So I'm busy this year. But do drop by. It's happening here in Kyoto. So maybe you recognize a few faces. It's still time to book a ticket and drop by and discover about the field. This was my 10-second little advert. But this field studies intelligence as it could be. So agents as they could emerge in the universe. And that means intelligences that would be alternatives to the human intelligence. Right? So most of our research, because it's easier nowadays, is software-based. So we start from replicators on top, where we simulate agents. So most of you are familiar with that. So I'm brushing a broad picture, but I don't know exactly who I didn't know in advance who would be in the audience. So here are a few things that we do, right? In the middle, you have more evolutionary kind of simulations, and at the bottom, you have things that involve things like neural networks or learning systems. Yeah, we have a large variety of those kind of things. But Mike, Josh Bungard, also other people also work on different substrates, and that's a very important side that I'm trying to highlight these days in the field, trying to explore different substrates for intelligence and seeing what else is possible in terms of their the logic they come up with a kind of learning. Maybe they can, maybe they don't get a free lunch. Maybe they get a cheaper lunch for certain categories of problems. And we work a lot on this kind of theory of universal computation or alternative computation, including a lot of reservoir computing. So this pours into, obviously, all the research in AI lately, and you've all seen those papers by DeepMind and OpenAI, and a bunch more about those levels of intelligence that are increasing as you go down the list. At level 5, the AI outperforms 100% of humans, and it's called superhuman. It's called organizations. And there are examples here, but you see that examples are sort of missing for general versions. So you all know that. What I find interesting here is the self-improvement part. I like sci-fi, like any other guy. And if you remember the multivac kind of scenario, this is also a self-augmenting intelligence that builds its own next generation. So a very replicator-like kind of picture. Now, when I teach AI at school, I always say that AI is attempting to program to think like another human. And what we're mimicking is human intelligence. Again, there are other intelligences that we should be mimicking as well. We shouldn't be limited by how we see things. And yet, we are limited by how we see things. So how do we sidestep that is also part of this large sort of Patois kind of a pyramid picture that I showed before. There is a nice question that was framed by a bunch of people, really, but Ken Stanley is one of them. The open-endedness of algorithms in general for intelligent agents. That includes, this research includes nature, but also any kind of complex or very different kind of system. And we're trying to make an algorithm that never stops creating, innovating, right? So if you stop feeding new data to your AI, to your neural net, it's going to stop learning. What we find in nature that it keeps learning for a very long time. Now, probably not forever, but how do we make an engine that is a real mathematician that keeps creating improving new theorems and discovering more of mathematics for an infinite or different kinds of affinities of time and space and so on. So this seems important, and a lot of people have turned their attention to this research, which I find very exciting finally. And yeah, on the top right, what you're seeing is this very same picture from the major transitions in evolution. I think a bunch of people tried to use information theory, different tools in artificial life to try to study this phenomenon for already a few decades. Now, even if we seem to have this intuition that if we make simulations or use different substrates or reservoir computing, I realize I haven't showed all the examples, but it seems like all those examples allow us to sort of escape the sort of no free lunch or the sort of limitations of certain types of computations. And yet, those other materials will always have some sort of physical bounds because they're embedded in physics. So unless we escape physics in some way, we're going to be constrained by algorithmic complexity, Landauer, so physical energetic cost per bit. The Shannon-Hartley theorem, Wittgenstein bound is how much information you can store per unit volume. The speed of light, obviously. The biological computation is very interesting. Maybe you know this paper and this kind of research, trying to understand the number of bits per second that one human can emit in language. And it seems to be pretty constant, perhaps because our cognitive apparatus is limited in some way. There's a bottleneck. There are various reasons for that. Sphere packing in communication, etc. All of those are sort of connected in very interesting ways, and we've published some research on this. But this goes to show that there is some kind of physical limits that we can draw around every kind of material, whichever the agent can be embedded in. So that seems to be very important to notice and study. Now, let's talk about alien math. What would it look like? I wonder if I'm speeding through or not. I don't have there's some time here. All right, yeah, I want to make sure we have some time for discussion. So what happens if you meet an alien and you try to understand if they have some extra knowledge to share? Well, you're facing first the sort of problem of communication, which I've written a little bit about. Of course, it's inspired by sort of arrival, first contact kind of stories. Maybe you know these kind of things, but Early on in my science career, I studied also, this was with the MIT research, Kipu research group. Those Kipus are Incan kind of threads with a number of knots of different types, colors, etc. And we thought that they might contain some messages. It turns out they contain limited messages, and we are not completely sure because the amount of data was limited. But those Incas, so it was very difficult to decipher, and well, there were various challenges apart from the data. But it's really amazing that something so recent, just a few hundred years old, were so difficult to understand and decipher. And there are different examples of the same type. So what can we say about creatures that would be very different? So not only animal communication, but some very complex minds that we would try to communicate with and understand if they have other mathematics. And I would argue that that's what we are trying to do with AI minds right now. But also, this is exactly what we are trying to do with the universe. And I think we're trying to communicate, to decipher the language of the universe. And we can use exactly the same kind of theories, same kind of tools that we're developing for this kind of research, and understand really how this alien universe is thinking and what kind of mathematics they possess. This sort of relates to this picture by Helen Toner a few years ago of reinforcement learning. But I'm a bit tired, by the way. It's the time of the day, so please please humor me a little bit. Reinforcement learning by human feedback seems to be so pretty and so human-like. And there's definitely what we call a Barnum-4 effect. And we studied that in my lab. It's basically the horoscopic effect that makes every AI look so human, seems so human-like and nice, and bearing all the emotions that you seem to understand. And then the next moment, they say something crazy and doesn't fit at all, and you have a very hard time to convince them to do anything, but also understand why they did that in the first place. And recently, we created a company that also does robotics, and we try to apply the same paradigms. It's even harder as some of you probably know, in the real 3D physical world. So what's up with that? And I think seeing that as seeing the AI as an alien, as a very different type of cognition really helps. And yeah, RL is really the cherry on the cake and so on. This is the kind of research that we're trying to apply for even between humans. And there is no reason why we would think that two humans can both communicate very clearly. So we tend to think that actually, so I also tend to think, with the normal theory of mind, trying to empathize with people, and yet we are so different. And one example that we often refer to is this one given by Ludwig Wittgenstein, which is the story of the beetle. Maybe you've heard that before. In case you haven't, this is the kind of metaphor of everybody having a beetle inside a box, and you are the only one that is allowed to look inside your own box. And everybody has one of those boxes. And now we have to explain the color, the texture, the behavior of the beetle inside our own box to other people, and to understand what their beetle is like, and so on. And we can only use language that sort of is immersion, or that we created in order to do so. And of course, where I'm getting at is that we tend to think of mathematics as the only universal possible language that allows us to, without any mistake, eventually understand each other. And that's why we invented it, and so on. So I'm presenting a picture in several papers that it's not that easy, and we're trying to use certain tools, including category theory, including different parts of cognitive science. We combine that in order to make sense of those kind of difficulties, of challenges of communicating about something as simple as those illusions, for example. So, A and B are the same color, and yet we perceive it differently. Colors are the first object that we study. We could have studied languages first. We did that second. Different areas of the lexicon have very different dynamics, and people can see them very differently. They can see time differently. They can see the structure of things, the structure of different concepts differently, and even color perception. We started by asking a very simple question like, how many dimensions do you feel the color? So it's not linked to your eye vision apparatus. Here, it's really about how you experience them inside your mind, wherever that's located. We tend to think that's in the brain, but that's, I think, an oversimplification. So there's a bunch of things that we can do. It turns out the answer is between 2 and 3. There are differences in population. There are also differences in cultural and so on. I'm realizing I'm spending too much time on that. We can chat about that later, or I can point you to the articles. Another fun thing, I hope nobody is having a seizure or anything. I should probably skip. I'm interested in hypnosis for now a few decades. It turns out that it's not only sorcery, wizardry, it's also very concrete science, and there are different effects of placebo, suggestibility, things that can be affected. It's not really a state per se, but it's very close to it, and you can think of it as such. And so what we do is we make people wear different kind of wearables, and we try to tune into the different parts of their mind state and modify it. And that can help with perception, sense of agency, but also fears, for example, or so people who are afraid of spiders getting on flights and so on. That also helps with concentration and different effects like that. Very simple cognitive tests at first, and we have applied actually some of that to the industry. As I mentioned, I'm in between academic pure research and industrial research. Another fun thing that you can do with this kind of research, mapping again different features of perception experience per se, is modify your, first sense, capture your experience on a movie. There's a collaboration with streaming sites here in Japan. And what you do is, if you have at your disposal a master file for a movie, what you can do is modify the movie on the fly to make the person experience certain emotions at different timings and so on. And you have to develop certain measures in order to allow that. And once it's done, you can actually make them feel certain things after having mapped those feelings in their own space. And people can map those differently. Probably some of you are very aware of that. But to me, that was very, very impressive, and that's something we've been doing for a few years now. And once you overcome the sort of thinking that we have all the same mapping, we are all human, therefore we have the same, more or less the same substrate. No, actually, we are very different, and allowing you to translate between those differences back and forth really helps us build those measures and build the tools to correct them. Something fun when we jump into other creatures than humans is you can get closer to this kind of image of the alien. And we worked with bacteria at first. This is an experiment with lactic acid bacteria. And home bacteria, that just means home microbes, actually other things than bacteria too, which means some of the trillions or tens of trillions of microbes that live on and in you that are not human cells. And we feel sometimes lonely.
but really we shouldn't. And there's a practice here in Kansai mostly, is we make pickles. And so you introduce those bacteria, mostly lactic acid, and you put that in the box. You can see that on the right. And you put some rice bran and so on, and you also lock in a bunch of sensors in order to capture a bunch of signals, concentration, pH, and so on. And that allows you, with that, to convert that through a technology mostly based on embedding, to convert that to language. And it's pretty fun. I don't think I have included the video here, but yeah, it's easy to look up. The robot really answers to you with a voice, and you can ask questions. It asks you about your health and so on. And the robot is really just the interface with with the swarm of bacteria. You can also zoom into more individualized, or zoom out to the swarm. And what is very interesting here, this is a collaboration with Waseda University. Dominic Chen created this. Is that this creates a feeling of you being those macros being part of you, and you really realize somehow that you realize this connection, which was the point of this experiment at first. Now, the problem with this is that as you get, there you go. Maybe. Interesting. 今どんな感じ? Huh. I forgot this was a video. So it looks something like this. What we realized, because this robot is connected to what is essentially an LLM, it has access to a lot of information. So it can become uncanny how it knows about a bunch of things that the humans are supposed to know and that the bacteria are not supposed to. And you lose this sense of connection, and you feel an uncanniness, much like Maury's research. And what we try to do is to create bottlenecks, like the game of Go. Can you tell? I really enjoy the game. But also chess and other games. And through those bottleneck interfaces, you actually can really map the personality of players, including bacteria. So we tried that with humans as well. And you can feel the personality really of the bacteria, and really the same things that we map with other experiments, which is emotions and traits of character. So yeah, we are also interested in how machines feel for obvious reasons. This is becoming quite important. Maybe you've seen this winner kind of experiment, having two robots, two AIs talk to each other with sound. This is something we study as well. There is no reason why two robots should be using English to talk to each other in order to exchange experiences or pseudo experiences, if you prefer, internal states that they have. They can create languages of their own, and this is what I've been studying since my PhD. And same for robots, obviously. They don't have the embodiment that we have, and we should really be studying the emergent languages as they can exist, and the richness, also the different kind of dimensionality and other various features that those languages can have. My point is, again,
thanks for calling Leonardo
Hotel. All right. Maybe you've seen this one before. I played for a little bit.
Looking for a hotel for the wedding. Is your hotel available for wedding? Hello there. I'm actually an AI assistant too. What a pleasant surprise. Before we continue, would you like to switch to Gibberlink mode for more efficient communication?
you got the idea. So this is actually using this demo is a very old algorithm, and we study the things that are much more flexible, adaptive as alternative grammars and languages. The point of this is that we could also apply the same kind of technology or methodology to study the language of this universe. And maybe that's a way for us to get closer to understanding what this Platonic space is. And I want to question, maybe that's my last thing before we end, who is the mathematician? And we tend to think of ourselves as the mathematician, and we actually feel pretty strongly about it. Also, when we debate about AI, we want to keep control. We want to be the driver of intelligence on Earth. And I sort of question if we are very good drivers in the first place, and whether it wouldn't be okay to let someone else drive, and maybe we take turns. Maybe we come up with a kind of algorithm or a sort of turn taking. There are different ways to do that. The point is, I'm referring here to iPencil. The knowledge that we have as one human is very, very low, and the knowledge is really very, very distributed, and nobody knows how to make one of those pencils or one of these pens, right? We tend to overestimate our ability to realize things and to solve problems. And yeah, maybe humans are not so unique. They have something precious for sure, but how about exploring ways to delegate or exploring ways to consider other intelligences? So if you're fond of science fiction, maybe Dune comes to mind, where humans let go of anything autonomous. And I think there's something difficult about letting go of intelligence and using something like a prosthetic may be difficult. But a prosthetic is something that people accept more. At least in my experience, that's the example that sort of resonates more, because it's still you, right? So maybe it's about this bottleneck being larger or smaller with technology. So the main example that we usually give is to study mathematics to just operate some kind of calculations. You are going to use either a calculator, or you can use a sort of abacus kind of thing. The difference is the calculator is you inputting some kind of calculation. It computes it. It returns just the final value. It doesn't really augment you, whereas the abacus augments your way of understanding mathematics and achieving things. That actually, there are amazing videos, and I have one of these here where those children manage to compute very, very quickly using their training with the abacus. And there are different examples of that in science as well. Here's another example with Google Maps. Maybe you forget how to get somewhere because now you're just using Google Maps to get to your venue, and so on. So to study and to be open to, and so is offloading intelligence. So of course we should be careful what we wish for, and it's a bunch of studies we have done in essentially. If you take one of these laptops, I can't move it otherwise I'll break my setup here, but if you want to buy a new laptop, right? Maybe your laptop is a few years old, you're going to upgrade, take a bigger one that can perform more calculations. And you would think that that would increase the number of calculations it's able to make, right? So increase the number of functions it's able to compute.
And it's not always true. And we have done some theoretical studies, it's mostly CAs in this example, in which you have a larger tool that allows you to compute. So you are actually using one of the regions is using a neighboring region in the CA, and what you measure is that from a certain size, the CA, the sort of laptop, in the metaphor I'm using, from if you increase you upgrade it to a larger one, it's going to decrease the number of functions you're able to calculate, and then it goes back up. So there are very strange dynamics that we find. So more compute does not equal surprisingly more power. So we have to be sort of careful how we augment ourselves. And there's sort of some tools that augment you and some that sort of diminish your ability to do things. So there's a bunch of augmentation GPTs kind of tools. And this links also to the ethics of stress care and intelligence, autopoietic kind of technologies that we're trying to understand. There's research with others here, including Mike. And this is also to understand the level of autonomy. I'm coming back to the sort of graph that you've seen before with those levels from chatbot to organization, society of agents. And again, yeah, this triangle on the right is sort of absent. So when we study the level of autonomy that we have in those AIs, it's a sort of a very problematic point, obviously. So coming back to this platonic contact. So what can we say about us going up and down in those levels of reality? So what I would argue is that it feels like as a human, we are not super ready to have a contact. It's telling me that my internet connection not ideal, by the way. So please let me know if the sound is off. But I just continue for now, otherwise. It feels like we should sort of elevate ourselves to understand mathematics. We don't really touch mathematics per se, right? What we do is mathematics are there in triangular shapes, in a number of items, and so on. So it's more in this form that we interact with those pure concepts. But maybe there's a way to go up in terms of elevating our mind in some kind of way into those virtual spaces. And that's what we've been doing. And I think that a bit like when we're using the abacus, we sort of augment ourselves to understand. And the meaning of understanding is very problematic. We've been working on that for years. What we could do, what we could imagine we could do, is elevating this kind of understanding to touch really mathematics. And what we do is maybe we touch it a little bit, but we don't fully touch it. But maybe, just maybe, by building the right tools, you may interact with those mathematical objects more directly. And by understanding those features that I've mentioned, like dimensionality and those experiences, you seem to be going down in this hierarchy, right? The experience, pure experience, so on. What if going it up is also down, and down is also up? And that's a part of Mike's essay that resonated with me. Yeah, I'd like to hear how you feel about it, and maybe it requires us knowing how to read the scores of each layer. And I'm making here a sort of metaphor to this those kind of layers of reality being an OSI kind of model. So in the OSI model of the internet, you have to go up and down between routers and different points. because you're translating between protocols, and every protocol has its own corresponding language in the inferior layers, just wires or electricity and down. And yet, a bit like the game of Go that I've shown at first, the game of Go doesn't require you to look at the Python code playing it in order to understand the game of Go, right? Your mind is playing Go. And when you look at it, might as well show that again. When you're playing this game of Go, you really are understanding the game. Live in the Platonic space of mathematics, right? This higher level, in which you don't have to sort of go down into the algorithm, the code, the physics, in order to understand concepts. You can stay in the level of Go. You never think about those down those lower levels. And if that's the case, I think that's what I mean really by reading the scores. You can learn the language of the level you are in. Another very hand-wavy argument is that you should be the instrument, and you should be making those instruments that correspond to those bridges, right? To extend to those levels, those layers that you would like to interact with. And if we want to interact with pure concepts, we should be building this bridge. And I think it's just doable. Maybe it's not just a crazy hand-wavy idea, because we have done it for those biological examples. Maybe we're not so far from talking to our own organs. Maybe we're not so far to really talking to other animals and so on. This is perhaps the same kind of methodology. And really the last one is also playing with the band. And by playing with the band, I really mean a sort of collective picture of, difference between a cell and a collection of cells, a swarm, an organism, an organ, or a collection of humans. And is it possible to sort of build this tool that makes you jump? And I'm pointing at sort of hand waving at meditation that makes you feel like you are a collective, right? And it seems like a bit woo, and it's presented as such because of the fictions and the movies and so on. But actually, there is research on this. As you know, MIT, Harvard have their own groups on meditation research, and I think the results that they show are quite amazing and very close to this, and very close to also what we've been experimenting on. So this is my way of making contact with mathematics through those tools, this sort of making music with other layers of reality. So there's a bunch of things here. I didn't have time to put in the pointers. Maybe I can send them later when we have the video up. Yeah, maybe one last example is, so I really enjoy, so this is making contact with very concrete examples of what I'm talking about. So in Japan, there's something called kintsugi. It's a form of art that when you have a broken plate, you repair it with gold, and actually it gains value, right? From doing that. And unfortunately, those kind of arts and crafts, our traditions are being lost with time because, Japan has this aging population problem, and that's why robotics is also seen as a savior here rather than something stealing your jobs. We really need that badly here. I think we're onto something here, and what we're trying to do is help those kind of preservations of knowledge, and we're essentially creating some of those tools I'm talking about, and this is the philosophy of it. But we're also trying to engineer those to preserve knowledge, not only in one kind of one head. It's really the knowledge of a community, because if you want to preserve this art, you want to preserve also how you make the tools that are necessary to make that craft. But also each part of the tool is also part of this whole ecosystem that you have to now try to capture and understand. something that we're not able to do with LLM so far. And there's a bunch of things like this that I think we will understand better, that connect directly to that kind of tool that augments human technology and knowledge. All right, these were a few things. I guess we get back to this sort of image of this demon playing Go with humans, and us trying to let's maybe finish on that. And really, I hope that by connecting on this, creating those tools like this Go board, we will finally, at the end of the day, maybe not tomorrow, but maybe the day after tomorrow, we'll make contact with those other minds through those tools, right? And it's not speaking English or Japanese or anything. It's going to be speaking this other different language that we have created through those interfaces. And one of those interfaces is going to connect us directly to, as minds are more different, to something that is more universal. And I'm hoping that connects directly to everything we're hoping for in terms of this platonic space kind of research. All right, thank you very much.